Hi everyone, welcome to lesson 15 of the Advanced Higher Stats course. In this lesson, we will be covering confidence intervals. You'll find this skill on page 26, 27, and 28 of the Advanced Higher course spec. By the end of this lesson, you should know what is meant by a confidence interval. You should be able to calculate confidence intervals at different percentages of significance. You should be able to calculate the confidence intervals for normal distributions, t-distributions, and sample proportions. And you should know the criteria required to calculate a confidence interval. In experiments and hypothesis testing, you need to disprove a null hypothesis, and the way you do that is by having a significant difference in your values. For example, if drug A treats 80 out of 100 cases, but drug B treats 90 of 100 cases, how do we know that wasn't a fluke? How do we know that next time drug B could treat 78 and drug A can treat 86? The way we see the difference and the significance of the difference is through confidence intervals. So working with that drug B question again, let's say if 90 was the median value, what we would calculate when we calculate a 95% confidence interval is the range in which 95% of the values would lie if we did the experiment multiple times. What that means is if we did the experiment again, testing drug A and testing drug B, we would expect drug B to be in this 95% confidence intervals 95% of the time. So if we did 100 times, 95%, 95 of those experiments will have the drug B outcome being in this range here. Now let's put this into practice. A sample, size 20, shows that the average weight of a turtle species is 194 grams. The known average is said to be 200 grams with a standard deviation of 15. Has the average mass of turtles significantly changed at 95% confidence? The first thing we do here is we calculate a 95% confidence interval and we follow the formula up here. So x bar plus or minus 1.96 times sigma over root n. And in this situation, that is our sample average, which is 194, plus or minus 1.96 times our standard deviation, which is 15, and our sample size, which is root 20. And the reason we're using 1.96 is because in this table here, 1.96 will leave 2.5% on the outside, if that makes sense. So if I draw this graph, there will be a 1.96 cutoff here, which would split the graph into 97.5% and 2.5%. But because we're doing plus or minus in this formula, we cut it off in this part here. So instead of it being 97.5%, this will be 95%, which is our confidence interval, and we'll have our 2.5% here. Now, if we get the answer to this formula, the upper limit would be 200.6 and the lower limit would be 187.4. So this means 95% of the, if you do the sample again, a sample set of 20, 95% of the average sample mean would lie in this range. And since the upper limit, 200.6, is greater than 200, we cannot say that the average mass of turtles has significantly changed. Now let's do the same question, but with one small twist. That is, it's asking for a 90% confidence in this time and not 95% confidence interval. So instead of using 1.96, where there would be a 5% kind of remaining on the side, we'll go for 1.64, where there's 10% on the side and we have 90% confidence. And it's exactly the same thing. So 90% confidence interval is equal to 194 plus or minus 1.64 times 15 over root 20. And for the upper limit, we will get 199 0.5, and for the lower limit, we'll get 188.5. And since 199.5 is smaller than 200, we can say at 90% confidence that the average mass of turtles has significantly changed. So there's a 10% chance that we've just proven a wrong positive here, but there's a 90% chance that we are correct. Now let's find confidence intervals for t-distributions. And the reason we ever do this is because we do not know what the true standard deviation is. A sample of size 20 showed that the average mass of a rabbit species is 1.1 kilograms with sample standard deviation of 0.3. The known average is said to be 1.2 kilograms. Has the average mass of rabbits significantly changed at 95% confidence? Well, here we can copy down the formula. The 95% confidence interval for t-distribution is x bar plus t n minus 1 0.975 s over root n. So what that means is we have 1.1 kilograms plus t n minus 1. So t19 is what we're looking at a 0.975 category column. So that means n is 19 and 0.975. So we will get 2.093 as our p-value. 2.093. Now we times that with 0.3, our sample standard deviation, over root 20. And the limits we'll get are 1.24 for the upper limit, 0.96 for the lower limit. So what that means is since 1.24 is greater than 1.2, we can't say at 95% confidence that there is a significant change in the average mass of these rabbits. Now let's do the same question but at 95% confidence. Here we just write the same formula again. 95% confidence interval is equal to x bar, which is 1.1 kilograms, plus or minus the t-value, and the t-value is still 19 as the row, but instead of 0.975, we will be using 0.95 because this will cut off 5% on both sides, totaling 10%, so will be 95%, 90% confidence. And that means our value is 1.729. And then we times that by our sample standard deviation, which is 0.3, over our sample size square rooted, and that will give us 1.22 and 0.98. And since 1.22 kilogram is greater than 1.2, we still, even at 90% confidence, we still can't say that the average mass of rabbits has significantly changed. Now, the final confidence interval we have to cover is for semi-proportions. A new policy has been established. 140 out of 200 people support the new policy. Calculate an approximate 95% confidence interval to prove or disprove if most of the population supports the change. First thing we do here, before we even calculate the confidence interval, is to see if our three criteria match, which allows us to approximate a confidence interval. And those three criteria are: is n greater than or equal to 20, is np greater than 5, and is nq greater than 5. Well, n is 200, so that the first one passes. np, we have that is 40 for us, and nq is 60 for us. So both of them are greater than 5, and we can carry on with the question. 95% confidence interval is equal to p hat, which is 0.7 plus 1.96, or plus or minus 1.96, times pq, which is 0.7 times 0.3 over the sample size, which is 200, and we square root all of that. And the limits we get for that is 0.76 as our top value, 0.64 as our lower value. Since 0.64 is greater than 0.5, the majority of the population does support the change and the new policy. That is the end of the lesson. Now you should know what is meant by a confidence interval. You should be able to calculate confidence intervals at different percentages of confidence, and you should be able to do so for normal distributions, t-distributions, and sample proportions. And you should know what criteria is required for you to do this for those three different scenarios.